Hey, g'day students. Welcome to our lesson today on industrial chemistry. We're looking at this idea that reagents and reaction conditions are chosen to optimize the yield as well as the rate for chemical synthesis processes. So there's compromise between equilibrium position and rate of reaction. So this is going to include today, we're looking at the synthesis of ammonia, and that's called the Haber process, which was done over 100 years ago now, and sulfuric acid, which is the contact process. So Fritz Haber was a German in 1918. If you remember a little bit of your world history, that was the outbreak of World War I. And so he was controversially given a Nobel Prize for chemistry for his role in nitrogen fixation in the air. However, it's controversial because he was a German and the Nazi party, and so there's still quite a bit of controversy about that. But very clever man. If you want to read about that Nobel Prize thing there, I just found the nobelprize.org and had a look at his little bio there. So that's worth a little read. Now, he was given this Nobel Prize for his role in the nitrogen fixation in the air, and he created a process which is now called the Haber process. Sometimes you'll see it called the Haber-Bosch process, and you'll know that with your power tools are called Bosch, and a lot of tools around your house. Essentially, what that's going to do, it's going to combine hydrogen with oxygen. Hydrogen with nitrogen from the air to produce ammonia. And so we can then create ammonia and collect liquid ammonia. Now this is quite important because in the ground are nitrifying bacteria, and so if you would have done a little bit of agriculture, you would have heard of these plants called legumes, with these bacteria called rhizobium in their roots. You go outside and pull up a clover and you'll see these little pink nodules on the roots, and that's where those rhizobium live. Anyway, Fritz Haber, I should say, invented this process 100 years ago and got that Nobel Prize for it. What that has done is he's been able to put nitrogen fertilizer then onto farmland, and what that has hugely increased our yields. And so that means what the earth can now sustain a population of 5-6 billion, I think it was. I'm not sure on those stats, but it's certainly a lot more than what it used to be. And he's done this by fixing nitrogen out of the air and turning it into ammonia. So from the industrial plant, it can be used as fertilizer. Now the plants will turn that into ammonium, and it'll take part of the nitrogen cycle, and we'll talk about that in a little bit more detail later. Now we should also remember Le Chatelier. So we want to think about Le Chatelier and the equilibrium position and the Haber process first of all. So remember, in equilibrium, the concentrations of products and reactants remain the same unless a stress is applied to the system. So Le Chatelier's principle states that when a stress is applied to a system in the state of equilibrium, the system reacts in a way to reduce the stress. So if I've got, for example, reactant A and reactant B there, and you can see I've added some extra reactant extra reactant A. Read the graph properly, Mr. Beasley. I've added in some there. You can see the effect is to make more product. So if I put in more reactant, I'm going to get more product. That's the way that the system is reacting to reduce the stress. Now, we don't need to copy this. This is back in Unit 3 stuff, but it's good to remember. You remember an increase in pressure in a system, so in a closed container, it means the system will act to decrease the pressure. So if we've got on the left hand side here, I've got 4 gas particles. I've got 1 nitrogen and 3 hydrogen gas particles. If I increase the pressure, it means the system is going to act to go towards the less gas molecule. So it's going to act to decrease the pressure. So if I decrease the pressure, it's going to shift the reaction to the left. So if I decrease the pressure, the system will react to increase the pressure by favouring the side of the reaction with more gas particles. We also looked at equilibrium graphs. So you can see that if we make a disturbance, what's happening here? This is an example back in Unit 3, Lesson 2, so it's a long time ago. We have this Haber process here. We've got nitrogen plus hydrogen reacting to form ammonia. We add in a bunch of stuff. So in this case, we increase the concentration of nitrogen. We're going to get more of those particles colliding together. And so we're going to create more product. So we'll get more ammonium produced. So the Haber process, as we said, is just the combining of atmospheric nitrogen with bottled hydrogen, for example, to produce ammonia. And ammonia is just NH3. We're going to use 4 gas particles on the left, so 1 nitrogen and 3 hydrogen, to produce 2 ammonia molecules. So you can see we have a negative enthalpy, so it's an exothermic reaction. If we have a look at the effect of pressure, what will pressure do? It will favour, so if I increase the pressure, the system will react against that stress, according to Le Chatelier, to go to 2 gas particles rather than 4. It's going to favour the side with the smaller amount of molecules. So that's the right-hand side. So increasing pressure will favour the formation of the right-hand side. So it's going to drive the reaction forward. And now increasing temperature, it's going to have the reverse effect for equilibrium, because it's an exothermic reaction. So the forward reaction is favoured at lower temperatures. If I increase the temperature, it's going to favour the left-hand side because there's more energy in the left-hand side than the right-hand side. You can use a catalyst such as finely ground magnetite, so Fe3O4. That, of course, will lower the activation energy, which will increase the reaction rate, but will not have an effect on the equilibrium position. Now, high yields are favoured at high pressure and lower temperatures. So the yield is high at high pressure and lower temperatures. A higher temperature gives faster reaction rates, though, so a compromise is made in industry. So if you're going to increase the temperature, you will actually increase the reaction rate. So that table I copied is a little bit dodgy there. That should be a decrease, shouldn't it? So decrease. So the actual conditions in industry is just 1 to 250 atmospheres, a moderate temperature of around 450 degrees Celsius, and a magnetite catalyst. But there are some other catalysts that we're about to talk about. So a promoter is a molecule that can increase the activity of a reaction. It will also affect the temperature of a reaction. Now, a promoter will, for example, create small pores in the catalyst, in this case exposing more iron ore crystals and therefore a greater surface area. So the most commonly used one is iron oxide, and mixing that with, whoops, that's a black highlighter, mixing that with potassium hydroxide. So that's the most widely used one. Now, ruthenium metal is a higher cost, but it's more effective. It does allow for a lower temperature and much lower pressure. There's some metal nitrides which have been modelled on the next thing. So the metal nitrides, for example, we've got iron and molybdenum there. We've got a big cobalt and molybdenum in that one. Now they're cheaper than the ruthenium metal, but they're 3 or 4 times more effective than the iron oxide and potassium hydroxide promoter. Now, the ideal is what's happening in nature. What's happening with these nitrogen-fixing soil bacteria and turning that into ammonia. So NH3 plus, NH3. So ammonia is important, therefore, too, in your soil. So if you grow legumes, which are these sorts of plants with these nodules, they'll have this, as I said, a bacteria called rhizobium, and in these rhizobium they have these enzymes called nitrogenase. And now the nitrogenase is an enzyme found in these nitrogen-fixing bacteria that contains clusters of sulfur, molybdenum, and nitrogen. The second process we're going to talk about today is just the manufacture of sulfuric acid. So this is called a contact process, and it's used in the industrial manufacture of sulfuric acid. So what you can see here is we've got two sulfurs and we're reacting them with oxygen, so we're burning sulfur. We're also then going to add water to produce sulfuric acid. However, it's a three-step process and there's a few steps involved in each. So the first step is just the production of sulfur dioxide as sulfur is burnt in an excess of air. Or you could combust a what do we call them? A pyrite molecule. So for example, iron pyrites there. So we've got 4 iron sulfides there. So that's pyrite plus 11 oxygens to get 8 sulfur dioxides and an iron oxide there, which looks a lot like rust, doesn't it? Now the second step is where we're going to talk in a bit more detail next slide. So we're converting sulfur dioxide to sulfur trioxide. So we're just going to react sulfur dioxide with oxygen and then we're going to produce sulfur trioxide. And the third step is going to be converting sulfur trioxide to sulfuric acid, but there's a bit of a middle step here. You can see we've got sulfur trioxide and we're reacting it with sulfuric acid to produce a substance called oleum. Now oleum is much safer to handle, so it's stored as oleum and then later on you can mix the oleum with water to produce sulfuric acid as you need it. Now looking back at step 2, just the conversion of sulfur dioxide to sulfur trioxide. So we've got 2 sulfur dioxides plus an oxygen. We should be producing 2 sulfur trioxides. So remember that the effect of a catalyst will have no effect on equilibrium yield, but it does lower that activation energy and increases the rate of reaction because it finds an alternative pathway. Now the catalyst used in this is vanadium pentoxide, and the catalyst ensures that actually you can produce enough quantities of sulfuric acid as for commercial applications. Now if you decrease the temperature, it's going to increase the yield, but it will affect the reaction rate too. It should increase the reaction rate if you did that again. So I just checked that one. It should actually change that by increasing reaction rate because we're increasing the number of collisions. So let's just check that. I think that's a decrease. And then we're going to increase pressure. Well, of course, that's going to force those particles together for an increase in reaction rate. But it will also shift the reaction to the right because there's 3 molecules on the left and 2 on the right. Increase the concentration of oxygen. Well, you're adding a reactant, so it will increase the reaction rate and it should shift that reaction towards the products if you're adding a reactant. Finally, this is not in your textbook, but we've talked about 2 processes today. We've talked about the Haber process and we've talked about the contact process. So there is an agricultural application for this, and that's if you mix ammonia and sulfuric acid together, you get this fertilizer called ammonium sulfate. So are you able to understand that reagents and reaction conditions are chosen to optimize the yield and rate for chemical synthesis processes, in particular the production of ammonia and sulfuric acid. When you are, please work on the mastery questions.